All right, today we're going to look at universal gravitation, talk about an equation and what it all means. Let me get my pen going here. All right, now we're in business. So the idea of universal gravitation came from Newton's mountain idea. And so if we were on the top of a mountain at the top of the earth and we launched a cannonball, some velocities would force it to drop straight to the ground, like at letter A. Some, if we sped it up, would go almost all the way around and stop at B. Some, if we launched it with just the right velocity straight out at a tangent, would go a complete circle and come back to where we started. And really the idea is that as we increase launch speeds, they would travel greater distances before falling to the earth. At some point, though, they would fall around the earth instead of into the earth. And that was Newton's idea of how gravity worked, or a very, very easy idea of how gravity worked. If we look at an apple dropping, and we just take a look at, on Earth, at the surface, the acceleration due to gravity is 9.8 meters per second squared, same number we've been using forever. Now, if we take the radius, okay, to the moon, all right, 60 times the radius of the Earth on the apple, let's say, and then our gravity, the acceleration due to gravity on the moon is 0.00272 meters per second squared. Huge difference, right? And this moon is not our moon; it's just a random moon that we came up with. But the point is that acceleration due to gravity changed a lot as we increased our distance from our object. Now, we're not just talking about the surface of the Earth here, we're talking about the center. So anytime we talk about gravity, we're talking about from the center of the object, the center of mass of the object, if you will. So mathematically, this is what we came up with. The force of gravity is proportional to 1 over the distance squared separating the object centers. And again, the object centers, right? So if we're talking about an object on the surface of a planet, the radius of the planet would have to be accounted for. If it's in orbit around the planet, it would be the radius plus the distance above the surface. But it's the distance separating the object centers. Force of gravity, then, is proportional to the masses also. So if we have the masses, and we multiply them by each other of our two objects, the person and the planet, or whatever, and we divide it by the distance separating the objects squared, it would be pretty proportional to the force of gravity, but not exactly. We weren't getting 9.8 meters per second squared as our acceleration when F equals ma in this situation, but we got close. So what's the effect of mass on the force of gravity? Well, if the masses the distance stays constant, and if our masses are the same, the force would be F. If we double the mass of one of the objects, the force, to repeat, if we double the mass of one of the objects, the force would double, with the distance staying constant. If we double the mass of both objects, our force would be 4 times that of our original, with distance staying constant. If we tripled the mass of one and left the mass of one the same, the force would stay 3 times as much. So the masses multiplied by each other will be equivalent to how the force would change. Now, the effect of distance is different. So here's our standard. Our masses are staying constant, but our distance, if we double our distance, if our distance doubles, our force is 1/4 as much, which is 1 over 2 squared, 1/4. If our distance is cut in half and they get closer together, our force quadruples, and it's 1 over 1/2 squared, which will equal 4. Now, what if we double the distance and then double the mass of each substance? Doing so gives us 4 over 4, which leaves it the same, which means our force is the same as if both masses were 1 and the distance was just d. So we can manipulate either of those to change the force of gravity on an object. Now, to make things match what we saw mathematically, this is the equation we came up with, and there's only one major difference. the masses multiplied by each other divided by the distance squared is still there. But then we came up with the universal gravitation constant, which is the big G. And you can see this number in the units will work out to give us a force of gravity in newtons. But it's 6.67 times 10 to the negative 11. Mass, or meter squared, goes along with d squared, and kilograms squared goes with our masses. So you have to make sure your masses are in kilograms and your distances in meters, as always. And your force of gravity then will be in newtons. But this is the universal gravitation constant. Now for the long thing to read to you. Sample problems. Determine the force of gravitational attraction between the Earth and a 70 kilogram student if the student is standing at sea level, which is a distance of the radius of the Earth, 6.38 times 10 to the 6 meters from the center of the Earth. And that's an approximate number that we'll use for the Earth's radius. So this will be the Earth's radius. And this will be the Earth's mass. So we just punch numbers in. G are constants here. Mass of the Earth, mass of the student, and the radius squared. And what we get is 686 newtons. Now we want to take the same person on Earth, but we want to put it in an airplane that's 40,000 feet above the Earth's surface. This would place the student's distance at a little bit greater, right? 6.39 times 10 to the 6th. So if we look backwards here, we had 6.38 times 10 to the 6th. Now we're 6.39 times 10 to the 6 meters. But when we do the math and punch the numbers in, we get a force of gravity of 684. So we actually lose 2 newtons worth of gravity on us when we're in an airplane. So that's one way to, don't weigh yourself on an airplane, otherwise it'll be less than what it is at sea level. So how this 70 kilogram student is seen at different locations on the Earth. Sea level at the equator, 684.6 newtons. At the North Pole, sea level, 688.3. Now, and that's because the distance from the North Pole to the center is less than the distance from the equator to the center, because the Earth isn't a complete orb, right? It's kind of flattened in the middle due to the rotation. So you will weigh more at sea level in the North Pole than you will at the equator. In Chicago, which is a little bit above sea level, 686.2, not a lot. And the top of Mount Everest, 685.4 newtons. So you see the difference between Chicago and Mount Everest, minimal. About a newton's worth of weight. Now at orbit, at low Earth orbit, like what we see with some satellites and some other things, the space station, we're at 647 newtons, and that's it's less, but still only by about 40 newtons. But now if we go to the high Earth orbit, what we see a lot of satellites in, we get 15.5 newtons, so the weight's a lot less. The Earth's attraction to us on the moon, 0.19 newtons, because we're that far away, right, from the center, big distance. And now if we go to the far edge of the solar system, the Earth's attraction to us is like 10 to the negative 8 newtons. So negligible. Even on the moon, it's negligible what the Earth does to us because we're on the moon. So today, Newton's law of universal gravitation is a widely accepted theory. It guides the efforts of scientists in their study of planetary orbits. Knowing that all objects exert gravitational influences on each other, the small perturbations in a planet's elliptical motion can be easily explained. As Jupiter approaches Saturn in its orbit, it tends to deviate from its otherwise smooth path. This deviation, perturbation, is easily explained when considering the effect of the gravitational pull between Saturn and Jupiter. Newton's comparison of the acceleration of the apple to that of the moon led to a surprisingly simple conclusion about the nature of gravity that is woven into the entire universe. All objects attract each other with a force that is directly proportional to the product of their masses and inversely proportional to their distance of separation, and that's squared. The value of g, the constant, is an extremely small numerical value. Okay? Its smallness accounts for the fact that the force of gravitational attraction is only appreciable for objects with large mass. While two students standing next to each other will indeed exert gravitational forces upon each other, these forces are too small to notice. Yet, if we replace one of the students with a planet, then the gravitational force between the student and the planet becomes noticeable. That's why things on Earth don't go flying towards each other. That attraction is negligible because the Earth's attraction to us is so great. So, how do we find G, like the universal gravitation constant for Earth, right? So if we look at the force of gravity, and there's our equation. So here's the mass of the Earth and the mass of an object. We'll say a person. If we know that force of gravity is mass times G, then we divide m by both sides. We get G is equal to the constant times the mass of the Earth divided by the distance squared. And that's how we can find G on Earth at any point on the Earth. So if an object were moved to a location that is 2 Earth radii from the center of the Earth, right? So we're here, right? And here's the radius, and then we have another radius, so we're here. So this is where we're at. We just take 2 times 6.38 times 10 to the 6th, and we get 1.276 times 10 to the 7th. The value of G can be found, and we can find the acceleration due to gravity to be 2.45 meters per second squared if we're an Earth radii above the surface, which is significantly less than 9.8. And you can see this is a nice little graph, and it's kind of proved why there's a squared d at the bottom. We get this exponential function here, and you can see that as you get initially, it's a really big difference between 2 radii, but then when we get farther down, the difference between 4 and 6 radii from the Earth and how we feel the gravity of the Earth is negligible. So if we want to find a G on any planet, all we got to do is use the constant. We got to know the mass of the planet, and then we got to know the radius of the planet, and we can find the acceleration due to gravity on its surface.